Hello. In this chapter, we will study about the different models of the atom proposed by the scientists and about the alpha particle scattering experiment, distance of the closest approach, Bohr model energy levels, and the hydrogen spectrum. So the Dalton in 1803 proposed that the matter is made up of tiny indivisible particles called atoms. In 1897, experimental study on electric discharge through gases shows that an atom consists of the positive and negative charges. Later, in 1898, J.J. Thomson proposed the model of the atom. According to the Sir J.J. Thomson, the atom is a positively charged sphere of the radius 10 to the power minus 10 meter, in which the entire mass is uniformly distributed and is concentrated at the center. And the negative charge, electrons are embedded here and there as the seeds in the watermelon, or like the plums in a pudding. So it is also known as the plum pudding model. This model of the atom could not explain the origin of the spectral series of the hydrogen atom, and it could not explain the large angle scattering of the alpha particles. Sir Rutherford, the research student of the J.J. Thomson, performed the alpha particle experiment to probe the structure of the atom, which in turn led to the discovery of the atomic nucleus. The alpha particle is a helium nucleus having the 2 protons and 2 neutrons. So the mass of the alpha particle is 4 units and the charge is 2 times the charge of the protons. This experiment was done by Rutherford and his associate Giger and Master. It is a top view of the experimental setups used by them. It is a source, radioactive source, which is enclosed in a lead cavity. And within the lead cavity, there is a small hole through which the narrow beam of the alpha particle comes out and hits the thin foil of the gold nuclei. The thickness of the gold foil is about 2.1 into 10 to the power minus 7 meter. The alpha particles are scattered in different directions and observed through a rotatable detector and consisting of zinc sulfide screen and the microscope. This one is the side view of the same experimental setup. It is the source of the alpha particles. These are the lead cavity. It is a hole through which the beam of the alpha particles coming out and hit the gold foil and is scattered at the different angle. It is a movable detector along with the zinc sulfide screen and the microscope. When the scattered particle hits the zinc sulfide screen, it produces a spot of the light called scintillations. And by observing the number of the scattered particles at the different scattering angles, he made the following observations, and on the basis of the observations, he had the following conclusions. The observation is most of the alpha particle passed straight through the gold foil. As they goes undeviated, it shows that the most of the space in the atom is empty. Second observation, the sum of the alpha particles is scattered by the small angles. It shows that alpha particles being positively charged are deflected by the heavy and the positive region in an atom. It shows that positive charges and the most of the mass of the atom are concentrated at the center called nucleus. The very few alpha particles were deflected through the large angles. It shows that alpha particles which are traversed towards the nucleus, their speed gets decreased due to the force of repulsion, and ultimately or finally they come to the rest and moves in opposite direction. The graph was plotted between the number of the scattered particles and the scattering angle. This will be the graph. Here it shows that for the small scattering angles, the number of particles is large. For the large scattering angle, the number of particles is reduced. On this basis, he is calculating or estimating the size of nucleus. It is called the distance of the closest approach. The distance of the closest approach is a minimum distance between the alpha particle and the center of the nucleus just before it is deflected by 180 degrees. This distance is called the distance of the closest approach. As the alpha particle, when it is far away from the nucleus, has some kinetic energy. As it is moving towards the nucleus, due to the force of repulsion between the alpha particle and the nucleus, the kinetic energy of the alpha particle decreases. And finally, it comes to rest. When it comes to rest, at that time, the distance between the alpha particle and the center of the nucleus is called the distance of the closest approach. Now, when the particle comes to the rest, the kinetic energy of the alpha particle is converted into the potential energy. That is, at the distance of the closest approach, the kinetic energy of the alpha particle is equal to the potential energy of the nucleus at a distance r naught. So as you know, the formula for the potential energy, K Q1 Q2 upon r naught. K is equal to 1 upon 4 pi epsilon naught. Q1 is the charge of the alpha particle, which is equal to the 2 times the charge of proton. Charge of the nucleus, Q2 is the charge of the nucleus. If Z is the atomic number, then the charge of the nucleus is Z. The distance point is at R. The formula for the kinetic energy of the alpha particle is half mv alpha square, or we can take it as the K, that is the kinetic energy of the alpha particles. Now solve it for the R naught. R naught is equal to 2 E square Z upon 4 pi epsilon naught and the kinetic energy of the alpha particle. On this basis, the distance of the closest approach is found to be of the order of 10 to the power minus 15 meter, which is approximately equal to the size of the nucleus. Obviously, the radius of nucleus must be smaller than the above value. Thank you and have a nice day.